All right, welcome everybody to week 9, day 2. We're going to be talking about a new data structure today. We're going to be talking about the binary search tree, also known as the BST. This is not to be confused with the BTS, which is a Korean boy band of some sort. So the good news is it's going to look a lot like the doubly nested or the doubly linked list we've been doing so far. Now you got to Google BTS. So if we're making like our standard like doubly linked list. Sorry, after watching Glorious Bastards speaking the bad Italian, like I'm trying to mispronounce everything now. Let's say we have a doubly linked list. We have a node pointer next and a node pointer previous. Looks something like this, and we can make it a little bit better by like initializing the data to 0, and the next is 0, and the previous is 0. These are nulls. And we can make it even a little bit better by templating it. Template class T, and then instead of it being a int data, we can make it a T data. And instead of initializing it to 0, we can initialize it to the default constructor. And that's like a pretty good doubly linked list node class. So doubly linked, exactly. Buongiorno. So, grazie. Yeah, correcto. Such a good scene. So, yeah, now you might be wondering, like, why am I doing this instead of 0, right? If I made a node of ints named Bob, then it's going to initialize bob.data, right? So if I see out bob.data, what's that going to print to the screen? Do a little recap of templates. It's gonna what is 0 in Italian? I'll look this up now. It doesn't matter. Okay, so yeah, it'll print 0. But what if we did this? What is that going to print to the screen? What do you guys think? Still gonna print 0? All right. Bold plan, Cotton. Let's see how that works out for him. Segfault. Okay. So technically, I think it caught the fact that it was a null pointer. But yeah, it crashes because what's going on here is you're setting a string to be 0, not double quote. You're setting a string essentially to be null pointer. And this is one of the reasons why 0 should not be used for null pointer like I did here. Because if you screw up the type somehow, then you are setting a string to a null pointer, and that's bad because it tries printing out the string, it dereferences the null pointer, and it crashes. And this is actually a very subtle bug because a lot of times people will test their code with integers, and then you just sort of happen to use, a string and it crashes. It'll even work with double, but if you try using a string, you get a segfault. And so this is why you don't want to initialize things to 0 when you're using templates, because your thing might be a string, and strings can't be initialized to 0. They will explode. So the proper way of doing this is to do this, which is to say use the default initializer. Okay, so the default initializer for an int is 0. The default initializer for a string is empty string. And so if we use this, then we get empty string, nothing. And if we had this be an int, then we get 0. Okay, this is the correct way of initializing to 0 things using templates. Use the open close curly brace. It's great. It's nice. It'll save you some headache. That was actually a bug. That was actually a bug in my read library, actually. So my read library actually crashed on strings the first time I wrote it because I just, out of habit, I just initialized things to 0 instead of to open close curly brace. And there was actually a segfault in my library because I was just like, just out of habit, I initialized things to 0. Okay. So what else can we say about this? One of the goals that I'm trying to do in this class is build your proficiency with pointers. And so if we have like a for loop here, for int I equals 0, I is less than 10, I plus plus, and we say node pointer Bob equals new node, like that. This won't compile. Why? What's wrong with this line of code? Testing your template knowledge right now. We're getting to BSDs. BSDs are going to look a lot like this. We need to build up our competency first. What's wrong with this? Needs a delete? Nope. It's not compiling. If you don't have a delete, you're going to leak memory, and it's going to be kind of a runtime problem maybe. But memory leaks are not compiler errors as long as you're not in Rust or something like that. You need to be node. That won't help. Needs a type. Very good, Mo said. I need to say what it is a node of. A node of integers like this is what you want. And since I don't like repeating myself, a lot of times you just use auto like that. So then you don't need to repeat whatever is in the template parameter there because you don't want to repeat yourself. So now what's the problem? Otal? Up arrow, hit return again. Before 41, I'm scared of pointers. After 41, I don't fear pointers. It is pointers that shall fear me. Yeah, so this class, like you might notice I've been going kind of hard on pointers. And one of the reasons for that is because I need you to be at least proficient with them and kind of like understand them. And they're typically the hardest concept to grasp for students because they're like an extra layer of introduction onto everything. But you need them if you're going to do inheritance. And you need them if you're going to be building data structures and things like that. So they're kind of essential. In 45, you'll see that they're all just integers. So when you do pointers in 45, it's just an integer. If you add 4 to it, great, you're now pointing at the next element in the array. Add 4 to it again. Okay, I'm now pointing at the next element in the array. You can see there's actually nothing really to them. They're just integers. But you cannot do something like this. If I had a node, just do it on one line like this. If Bob was a node of string pointer, that doesn't work. Because a node pointer holding strings is not a node pointer holding ints. It's a type conflict. Even though under the hood, they're literally both integers. C++ says no, not allowed. Okay? Not allowed. Don't do that. And so the type system will catch errors like that for you. Right. So what is wrong with our code now? No, Otal, you had the answer before. Like at 240, you said the right answer. So what is the problem with our code now? Our code's compiling now, right? It's compiling. We got a runtime problem here. Where does pointers are just integers land on the C++ iceberg? It's pretty much hidden. Like you wouldn't even know that they're integers because they're heavily typed. And so a pointer to an integer is different from a pointer to a node of integers, which is different from a string, a C-style string, a constant char. Sorry, they're all different types. Under the hood, they're all integers. So, Rohan, what's wrong with our code? You need a constructor? Nah, we got a default constructor. Like this is this code here makes the constructor for us, essentially. We got a memory leak. So yes, we now need a delete. And we have absolutely no way of deleting this data because we've lost it, right? But by the time we get down to here, there is absolutely no way to recover any of that memory. It is gone. It is gone. It's been thrown in the volcano. That memory is gone until we quit our program. So if we were to compile our program, without an address sanitizer, it just runs and it works. Yay, good, everything's fine. But if we were to compile our program with address sanitizer turned on, fsanitize equals address, which I hope all of you use when you go on to greater things. Let's turn off the optimizer. Thank you very much. The optimizer is actually deleting all of that code so that we didn't leak memory at all because it had no point. So it actually deleted it. We didn't leak. But if you turn off the optimizer, then you can see here we have leaked a lot of stuff. We got a leaky bit of code, and we can compile this code with the debugging information turned on, and there we go. So on line 15 of main.cc, we are leaking memory. Now, a lot of students are going like, it should be 10, shouldn't it? Weird. So a lot of students are like, the address sanitizer is saying the problem is here on line 15, right? That's what's wrong with my code here. And the answer is nothing. This code is fine. I mean, it's not, but like it's fine, right? It's not the new that's the problem. It's telling you you're renewing memory here. The problem is you're not deleting the memory on the backside. So you need to make a destructor or something that will clean up after yourself later. So whenever you get a problem with a memory leak, it just tells you where the memory is coming from. It does not tell you where you should put the delete. Okay? And it can't really know. Because, like, it doesn't know. Right? Like, I don't know. Like, where are you going to... When are you done with it? I don't know. So that's why we have destructors. Destructors are there so that you can clean up after yourself. Now, and that's usually where your delete should go. Your news should be in constructors. Your deletes should be in destructors. And that's about it. You should pretty much never have anything else. No news like out in main like this. Don't do this. Okay. So we got our pointers here. And we got our news. We don't have a delete. So some students are doing this. They're like, all right, I'll just delete it here. Now, cool. We're not leaking memory now, but if we try using, Bob past this point equals 14. If we try using Bob past this point, what's the problem with this? What's wrong with this code? Bob's gone, but we're using it. It's compiling just fine. All right. I've deleted Bob and I'm using his data afterwards. Is this a seg fault? Yes or no? What do you guys think? Is it a seg fault? Nope, you're all wrong. It is not a seg fault. No problems. No seg fault. Bob is not set to null. If I had set Bob to null, if I set Bob equal to null, right? Now is it a seg fault? Isn't it random? It's not random at all. It's not random at all. What was being set to 42? It's not undefined behavior either. I mean, it is, but not in this circumstance, actually. Well, first of all, answer the question. Is this a seg fault now? Yeah. The rule is anytime you have a null pointer and you use the arrow operator on it or access its member variables in any way, anytime you dereference a null pointer, that's a seg fault. You're trying to access the minefield of doom at memory address 0, aka the 0 page. The operating system has it marked off limits. You try reading from it, the operating system kills your program. Okay? So here, we are trying to read from data at memory address 0, and that kills your program. Here, it doesn't, right? Because Bob is not changed by delete. Delete does not set Bob to null. Doesn't do anything to it. All it does is it marks the memory that Bob was using as being free to be reallocated at some point in the future. That's all it does. Okay? It just unallocates the memory. So Bob is still pointing to some location in memory. We haven't done any news yet. And so setting Bob points to data equal to 42 is bad, but it's not going to seg fault because Bob's still pointing at where it was before. That's inside of the data segment. We're fine. Okay. If we were to see out Bob, what is this going to print? This is really bad, by the way. Don't do this. But technically, I can tell you exactly what will happen. As long as you don't have a multi-threaded program, this isn't probably going to crash. Address sanitizer is, by the way, going to get mad at you for doing this for good reason. So listen to address sanitizer. This is called a use after free bug. Do not use a pointer after you've deleted it. So not a business. It's probably not. You're probably not going to have any problems with this until you make your program multi-threaded, and then it might very well explode on you. So, what is this going to print? If you print a pointer, what does it print to the screen when you print a pointer? What does that print? Integers? Yeah, it prints a memory address. And so usually you don't print pointers, but this can be interesting. And so what you can see here is that we are actually getting the same memory address over and over again. Because we're allocating Bob, we print it out. This any area that begins with a 5 on our system is probably going to be the heap. If you guys remember the picture. No. No. Sure. So high part of memory is stack. The 0 page technically is not part of the code segment. It's just marked off as unusable. Right above the bottom of memory, though, you have your code. All of your program is down here. The data segment and the BSS, which is where your globals are essentially, are held here. You've also got like a read-only data section that you can read from, but you can't write to. And then above that's the heap. So the heap is around memory address 5, 55, 56, something like that. The stack is up at the top of memory at 7F is the top of memory. So if I were to make a variable here, node pointer Bob, let's say node Bob, and see out the address of Bob like this. This is going to print out a memory address above the heap. See that? So that's the stack. That's the very top of memory, 7FFFFF. It's near the top. The heap is around 55, 56. The code segments down below. So usually don't point out, you don't print out pointers, but it could be useful. Like in CSI 45, I actually wrote this code in CSI 45 yesterday because students were wondering, are memory addresses consecutive when you do a linked list? Do they come out next to each other in memory? And you can see here, by deleting it and freeing it and allocating and doing delete, allocate, new, delete, new, delete, it keeps coming out on the same address. If we don't have a delete there, then you can actually see that the memory addresses are all consecutive in memory. And so students were just curious in 45 because it matters. If you have consecutive things in memory, it's actually faster. So we did this yesterday. We're like, look, if you do a linked list, by default, it'll, you know, if you got nothing else going on, all these nodes in the linked list will be right next to each other in memory. So the memory performance is not as bad as you think it would be. So you can print pointers like that. It's okay. All right. So the main thing is like, if you ever see like a pointer to like 7F in your data structure somewhere, your code's probably bad. You never want to have a pointer to a stack allocated variable hanging out with you anywhere. Okay. So that was a little bit of pointer review stuff, stack, heap, stuff like that. I'm actually going to create a second recording for today just to talk about binary search trees because we've been talking for like half an hour and I want people to be able to just jump right to the lecture on binary trees. So let me switch recordings now. Actually, it's been 18 minutes, but okay, whatever.